You know, if you really want to get good at programming, you've got to get inside the mind of the machine. So today, that's exactly what we're going to do. We're pulling back the curtain to see how a computer actually thinks.
I mean, have you ever really stopped to think about what's happening when you click on an icon? It feels like magic, right? But it's not. It's this incredible, super fast dance of pure logic. So come on, let's take a trip inside the machine and see how it all works. Okay, so to get a handle on how a computer thinks, we first need to understand the commands we give it. These commands are all bundled up into something we use constantly, a program.
Now the key word here is mechanically. A computer has absolutely no idea what you want it to do. It doesn't get the big picture. It just follows a program like a super detailed recipe. Every single step is simple, crystal clear, and it follows it to the letter. No creativity, no improvisation, zero.
All right, so who or what is actually following this recipe? Let's zoom in. We're going to look at the core parts of your computer to see where the real action is. So here we've got the two main players inside your computer. First up is the CPU, the central processing unit. That's the brain, the part doing all the heavy lifting. And then you've got memory. The best way to think about memory is like a massive wall of numbered mailboxes. Each one of those little mailboxes holds just one piece of info, either an instruction from our program or some data that instruction needs. And this simple little four-step loop is the engine that drives everything your computer does. The CPU grabs an instruction from memory, figures out what it means, does it, and then immediately does it all over again. Fetch, decode, execute, repeat. That is the literal heartbeat of your computer, and it's beating billions of times every single second. Just mind-blowing, right? So the CPU is ridiculously fast, but it has one big problem. It only understands one very, very specific language. And this creates a huge language barrier between us, with our complex thoughts, and these powerful, but also very literal-minded machines.
Okay, so on one side of this gap, you've got machine language. We're talking pure ones and zeros. It's the only thing the CPU gets, period. On the other side, you have what we call high-level languages. Think Java, Python, stuff like that, which use words and structures that we humans can actually read and write. But here's the catch. The computer can't run that human-friendly code on its own. It needs a translator.
And that translation job basically happens in one of two ways. You've got a compiler, which is like hiring someone to translate an entire book before you publish it. It takes the whole program and spits out a new version in machine language all at once. Then you have an interpreter, which is more like having a UN translator in your ear, translating each sentence one by one as it's spoken. But, you know, this whole translation thing created another massive headache for programmers, especially as all these different kinds of computers started popping up. But the folks who created Java, they came up with a seriously elegant solution.
And this was the million-dollar question, right? How can you get one program to run on all these different machines like Windows, Mac, Linux? See, if you compile a program for a Windows PC, the machine language it spits out is complete gibberish to a Mac. Back in the day, you had to literally rewrite and recompile your program for every single system. It was an absolute nightmare.
And this is where Java's solution was just brilliant. Instead of compiling your code for one specific machine, the Java compiler turns it into this universal middle ground language called bytecode. Think of it like a generic set of assembly instructions for a computer that doesn't actually exist. Then, each platform, Windows, Mac, you name it, has its own special translator, the Java Virtual Machine, or JVM, and that JVM's only job is to read that universal bytecode and translate it on the fly for the local hardware. It's genius! This amazing idea led to one of the most famous slogans in all of programming. Because of the JVM, you could finally write once, run anywhere. It was a total game changer. It achieved true platform independence. So this run anywhere thing was incredible, but it also opened the floodgates. Programs started getting bigger and way more complex. A new problem emerged. How do you even manage all that code? Developers needed a totally new way to organize their work. And that led to a new way of thinking about design itself.
Yeah, as programs ballooned from a few hundred lines of code to literally millions, that old model of just writing a long list of instructions, it just fell apart. It was totally unmanageable. The solution was a mental shift. We had to stop thinking of a program as one giant recipe and start seeing it as a system of smaller interacting parts, or what we call objects.
So what's an object? The big idea is that an object is a self-contained little bundle. It holds two things: the information it knows, its data, and the things it can do, its behaviors. So, for example, a user object in an app would hold data like a username and password, and it would also have behaviors like the ability to post a message or change a profile picture. See? Data and behavior all wrapped up together.
Okay, so if an object is the finished thing, what's a class? Well, the class is the blueprint. It's the recipe. Or, my favorite analogy, it's the cookie cutter you use to make the cookies, which are the objects. The user class is what defines the structure for every single user object, what they'll all look like, and what they can all do. Now, inheritance. This is where object-oriented programming gets really powerful. It lets you create a new class that's basically a more specific version of a class you already have. And the cool part is, this new class automatically gets all the data and all the behaviors of its parent. You don't have to rewrite anything. It saves a ridiculous amount of time and code.
And you can see that idea right here. You could have a general drawable object class that knows some basic stuff, like having a position on the screen. Then more specific classes, like a rectangle or an oval, can inherit that position property. They get it for free. They just need to add their own unique instructions for how to actually draw themselves. It's a super efficient way to build things up and reuse your work.
So let's just step back and put this all together. What do we have? We have a language that can run on any computer in the world, and we have a design philosophy that lets us build really complex systems out of small, reusable parts. That 1-2 punch, that powerful combination made Java the absolute perfect tool for building on the next great frontier, the World Wide Web. So why does all this matter? What's the big takeaway here? Well, for one, the next time you use an app, you'll actually understand the magic happening behind the screen. You can appreciate these clever solutions, like the virtual machine, that make our digital world possible. And maybe most importantly, you've now got the foundational mental map that will help you learn pretty much any modern programming language out there.
So there you have it. We've pulled back the curtain on the mind of the machine. From that simple fetch and execute cycle all the way up to the genius of the virtual machine and object-oriented design, you now see the landscape. You get the rules of the game. So the only question left is, what are you going to command it to do?